Hello students, and welcome back once again to the JCE Connect, to the online lectures of design of pre-stressed concrete structures. Okay, so we were discussing about the shear strength of pre-stressed concrete beam, and in the last class we have solved the problems over to calculate the shear strength of beam, and today's session also we are going to solve another types of problems to compute the shear strength of pre-stressed concrete beam. Okay, so I'll read the problem. A pre-stressed concrete beam of span rectangular cross section 120 mm wide, 300 mm deep, pre-stressed by parabolic cable, eccentricity 0 at support and 100 mm at center. Okay, pre-stressing force is 180 kN. Also pre-stressed by vertical cables imparting a stress of 2.5 Newton per mm square. Estimate the principal stresses at the support section. UDL of the beam including self weight is 5 kN per meter. So this is a given problem. Okay, so again it's a rectangular cross section of size 120 mm by 300 mm, and it is pre-stressed by a parabolic cable with 0 eccentricity at support and 100 mm at midspan. The pre-stressing force given is 180 kilonewton. Okay, it is given as 180 kilonewton, and also apart from that, this is the new condition added in this problem. Also pre-stress by vertical cables imparting stress of 2.5 Newton per mm square. So here this beam is also carries a vertical pre-stressing force, and which develop a stress of 2.5 Newton per mm square. They have not given the vertical pre-stressing force, but they have given that force develops a vertical pre-stress of 2.5 Newton per mm square. Estimate the principal stresses at the support section. UDL of the beam including self weight is given as 5 kN per meter. Okay, so apart from that, the UDL is given on the beam is 5 kN per meter, which is includes its self weight also. Okay, so this is regarding the sketch regarding the above problem mentioned. Okay, so here, so first of all, the theta is 4E by L. So 4, and the eccentricity at midspan is 100. L is 10 into 10 to 3, so it is 0.04. Okay, then first of all, we have to find out the principal stresses at support section. Okay, so we'll find out the stresses at support section now. So first is the direct stress. Fx is equal to P by A. So this is P by A. So P is given as 180 into 10 to 3. The area is 120 by 300. Okay, so we'll get this as, so this will get as 5 Newton per mm square. Okay, then also it is given as Fy. Okay, if I, so here it is given as imparting also the pre-stress by vertical cables, also pre-stress by vertical cables imparting a stress of 2.5 Newton per mm square. So the vertical stress is given because of the vertical cable, it is as 2.5 Newton per mm square. So therefore it is Fy is 2.5 Newton per mm square, which is given. I'll write given here, okay, which is given. Then next is shear stress. So this is regarding direct stress. Next is shear stress. Shear stress, that is tau v is equal to 1.5 v upon b t. Okay. So for rectangular section, directly you can find out 1.5 times v by bd. Okay. So this is for only rectangular section. Okay. Where v is equal to the reaction R, reaction minus the vertical force PV, reaction minus vertical force PV. So where the vertical force PV is taken as P sin theta, sorry theta. So sin we are neglecting. Okay. So this will be PV will be P theta. So P is 180 into 10⁻³ and theta is 0.04. So PV is equal to, we get it as 7200 kilonewton, sorry Newton, or 72 kilonewton. So that is PV, regarding PV. And the reaction is WL by 2 because it's a beam loaded with UDL. So also R is WL by 2. Okay. So W is 5 including the self weight, and the L is span, that is 10 divided by 2. So it is 25 kilonewton. Okay, 25 kilonewton. So therefore the vertical force V on the vertical shear V is 25, that is reaction minus PV. PV is 7.2 kilonewton, 7.2 kilonewton. 70 to 100 means 7.2 kilonewton. Okay, so the V is, will get it as 17.8 kilonewton. So that is 25 minus 7.2, 17.8 kilonewton. So we will get total shear V is 17.8 kilonewton. Okay. So now therefore the shear stress tau is 1.5, V is 17.8 into 10⁻³ upon BD. So B is 120 and D is 300. So we will get this value as 0.742 Newton per mm square tau. So the shear stress is 0.742 Newton per mm square. So now the principal stresses. Now the principal stresses are again F2. So we have to find out, estimate principal stress at support. Okay. So F is equal to, so it is F is equal to Fx plus Fy divided by 2. So that is Fx plus Fy divided by 2 plus or minus square root of half of square root of Fx minus Fy divided by 2 d square plus 4 tau square. Okay, 4 tau square. So here we know that Fx is equal to 5 Newton per mm square and Fy is equal to 2.5 Newton per mm square. Here we have already calculated Fx is equal to 5 Newton per mm square and Fy is equal to 2.5 Newton per mm square. Understood? Okay. So then, we are not concentrating about the plus sign by using plus sign because it is a compression. We have to concentrate only with respect to the negative. So that is because the tensile stress is developed in the concrete. Okay. So we have to concentrate only on the tensile stresses, not on compression, because when you use positive sign it will be compressive and when you use negative sign it will be tensile. So we have to concentrate for the tensile stresses. Okay. So I will note down, insert the equations, the values. So that is phi u plus 2.5, that is Fx plus Fy divided by 2 minus half of square root of Fx minus Fy. So that is phi u minus 2.5 divided by 2 whole square plus 4 tau is 0.742 square. Okay. So we will get this value F2 as the maximum tensile stresses are plus 2.296 Newton per mm square. Okay, that is plus 2.296 Newton per mm square. So this is regarding the principal stresses. Okay. Then next, suppose in the exam it is directly given as the stresses in the vertical cables are 2.5 Newton per mm square, but suppose if they give force in the cable, so that time how to calculate, that I will explain now. Okay, that I will explain. Suppose I will write a note. Alternatively, if vertical pre-stressing is done through vertical stirrups, provided at a spacing of 100 mm center to center, 100 mm center to center, carrying a pre-stressing force of of 30 kilonewton in each stirrup, 30 kilonewton in each stirrup. Okay. So in the exam, suppose if it is given like this without giving the pre-stress in the cable, like the above problem, it is given that the pre-stress in the cable is directly 2.5 Newton per mm square, but without that, if it is given like if vertical pre-stressing is done through vertical stirrups provided at a spacing of 100 mm center to center, carrying a pre-stressing force of 30 kilonewton in each stirrup. So in the beam, a vertical strap is provided at a spacing of 100 mm center to center, carrying a pre-stressing force of 30 kilonewton. Okay. Suppose if it is given like this, so what you have to do? So I will just I will draw just a plan. Suppose in the sketch, okay, a beam is like this. It is in plan, so this is a width of the beam, so it is 120, and the stirrups are provided, means stirrups in plan we can see the two dots because the stirrups will be like this. in the elevation. Okay, and when you look from the top plan, what you can see the dot, like the dots like this, or you can see like this. Okay, these are the dots you can see. So if the stirrups are provided at a distance of 100 mm center to center, like this, with the distance between the two stirrups is 100 mm center to center. So we have to consider the effective like this. So this will be again 100, because from center 50, again from this side it is 50. So this is also 100. Okay, so that time you have to find out Fy. Okay, like this. So therefore this is in plan of a beam with 120 width. So you can see the stirrups, like the stirrups are provided with 100 mm center to center. Okay, so we have to find out Fy is equal to P vertical, that is vertical pre-stressing force, divided by width into spacing, width into spacing. Okay, so the P vertical is 30 into 10 to 3, it is given here. The vertical pre-stressing force is given as 30 kilonewton. Okay, 30 into 10 to 3, and divided by width of the beam is 120, you can see here. So that is 120, and the spacing is 100. The spacing is 100. So this will be 2.5 Newton per mm square. This is Fy. So we can calculate Fy like this also if the pre-stressing force is given. Okay. Same way we can calculate like that. Okay, so I think you people have understood. Okay, suppose the pre-stressing force is given, so that time we can calculate the pre-stress, that is Fy, by like this. Okay, so for that the stirrup spacing should be required. So that we can use here and we can calculate Fy. Okay, thank you. Okay, so we will solve one more problem. So here in the problem it is given a pre-stress concrete beam of 150 mm by 300 mm parabolic cable, eccentricity of 0 at support and 100 mm at midspan. So the size of beam is 150 mm by 300 mm, and again the cable profile is parabolic with 0 eccentricity at support and 100 mm at midspan. The length of the beam is 8 meter and the live load is 2 kilonewton per meter. Determine the effective pre-stressing force okay. So determine the effective pre-stressing force to balance dead load and live load on the beam. Estimate the principal stresses at support section. Okay, so again it is a similar cross section and the cable profile. Okay, so we will start with the solution, no need to draw the sketch once again. Okay, so here we have to find out determine the effective pre-stressing force. One thing we have to find out the pre-stressing force to balance dead load and live load. So live load is given here 2 kN per meter, so we have to find out the dead load. Okay, so first I will write the given data. So the cross section of beam is given as 150 mm by 300 mm. Okay, and the WL it is given as 2 kilonewton per meter. So here first the dead load of the beam is 0.15 into 0.3 into 24, it is known as 1.08 kilonewton per meter. Okay. So now by load balancing concept, movement due to pressure is equal to external bending moment. Movement due to pressures should be equal to external bending moment, because to balance the load, external load. So the movement due to pressures is nothing but P into E is equal to the bending moment due to external load is WL square by 8. Okay. So here the W is equal to, here W is equal to 1.08 plus 2, so that is 3.08 kilonewton per meter. 3.08 kilonewton per meter. So therefore P into E is 100. Into 10 to minus 3 to make it in meter. So okay. So that is 3.08 into L is 8 square, W square by 8. This is 10 to minus 3 to convert the eccentricity in meter. Okay. So we will get the precessing force P is 246.4 kilonewton. The precessing force is 246.4 kilonewton. Okay. So first we have calculated, they are asked to calculate the precessing force. So we have what it is, 246.4 kilonewton. Now next is the principal stresses at support section. The principal stresses at support section. Okay. So we know that PH is equal to P, so that is 246.4 kilonewton, and PV is equal to P sin theta. So sin we are neglecting, so it is P theta. Okay. So where theta is equal to 4E by L. Okay. So that is 4 is 0.01 divided by L is 8. Okay. So this as 0.05. So 4E by L. So that is P is 246.4 into theta is 0.05. So we will get PV as 12.32 kilonewton. Okay. Now direct stress is equal to Fx, that is P by A, that is PH by A actually, PH by A. So PH is 246.4 into 10 to 3 divided by 150 into 300. Okay. So it is, you get it as 5.47 Newton per mm square. 5.47 Newton per mm square. Then shear stress, tau max is equal to 1.5 times V upon BD. So 1.5. So V here is again so V is equal to 0 here because it is balanced. Okay, because we are balanced by calculating the precessing force to 46.4 kN. Okay, so therefore tau max is equal to 0. Tau max is equal to 0. Then therefore F is equal to Fx plus Fy divided by 2 plus or minus half of square root of Fx minus Fy by 2 whole square plus 4 tau square. Okay, so therefore F1 is equal to 5. F is equal to, I will substitute here 5.47 plus Fy is 0 divided by 2 plus or minus half of Fx minus Fy. So Fx is 5.47 minus Fy is 0 divided by 2 square plus 0 because tau is 0 here. So we will get F1 and F2. So F1 is equal to, we will got it as 5.47 Newton per mm square and F2 is 0. Okay, so here we have got 5.47 Newton per mm square, same, because whatever the stress is developed due to the direct pre-stress which is calculated to balance the dead load and live load. Okay, understood. And F2 is 0 means it is balanced. The tensile stress is balanced and the whatever the compression is 5.47 is same as the direct stress because it is calculated to balance the load, that is the external load, dead load and live load. Understood? Okay, so this is regarding today's session. Okay, so thank you for listening. Okay.